Let's take a look. All right, we left off at question number 16. It says, with which reagents can the ketone shown be prepared via a Diels-Alder reaction? Remember that a Diels-Alder reaction is a 4+2 cycloaddition. 4+2 cycloaddition. And we know that we have to have a diene, and we need to have a dienophile. And so that provides us with a problem right away with A, because if we were to try to do a cycloaddition here, this would be a 2+2 cycloaddition, and so that wouldn't give us a 6-membered ring, right? We need to have 4 carbons, plus the carbons over here, 8 carbons, and so that won't work. It won't give us the 4+2 cycloaddition. If we look at B, we could get a cycloaddition there. Technically, we could do a cycloaddition. However, after you push the arrows here, you would end up with a bicyclic compound, wouldn't you? Right? You'd end up with a bicyclic compound where you have this like this, and you'd end up with a bridged compound. And I'm not going to draw the structure of that bridged compound because it's not right. If you look at C, this is also a 2+2 cycloaddition. So here we had a 2+2. Here we had a 2+2. Here we end up forming something that's bridged, okay? Whereas in D, if you just flip that diene around so that it looks like, this, it might be easier for you to recognize that once you draw the curved arrows here, like this, that you're going to end up with this compound where you have 3 fused 6-membered rings like this. You didn't touch this double bond. You made a new double bond here, and you have the 2 carbonyls like this, and that is the compound you were looking for from the get-go. And so the answer must be D. All right, let's move on to question 17, which deals with forming a carbon-carbon double bond, right? This is a Wittig reaction. Wittig reaction. And so we have to use these 3 reagents, but we have to pick the correct order. Well, the first reaction is going to be the one between the isopropyl bromide. So this is your starting material. You have isopropyl bromide. And the first thing you're going to do is you're going to treat that with triphenylphosphine. And this does an SN2 to make your phosphonium, right? You end up with this where we have our phosphorus with a positive charge on it, okay? Plus you have the bromide. That's your phosphonium salt. So that means that this is going to be number 1. Then this next thing you have to do is treat it with butyllithium. That's what this represents. This is butyl lithium, which is a strong base. And so what butyllithium would do is it would rip off this proton to make the ylide. So we would treat this with butyllithium. So we'll just write the butyl carbanion like this, and we have proton transfer occurring like this. And again, that's going to give us the ylide. And of course, you can draw the ylene form if you want, but this is the ylide. So we have the negative charge here and the positive charge on our phosphorus like this. And then in the last step of the Wittig, we're going to react it with the ketone. So we're going to treat it with the cyclohexanone, and that's going to make a bond between, you're going to remove this oxygen and you're going to remove the phosphorus to make triphenylphosphine oxide. So you're going to end up with this compound where you have the double bond here. There's no sister trans to worry about, but you're going to end up with this compound here plus triphenylphosphine oxide. So that's this triphenylphosphine oxide like this. So this is going to be the compound. So we went 1, 2, 3. So that means we're going to go 2, 1, 3. And so the answer is C. First we do triphenylphosphine, then we do butyllithium, and then we do the ketone last. And again, this is the Wittig reaction. And you can be sure that the Wittig reaction will show up on your final exam, or at least you can be 95% sure that it will. It's such a common reaction in organic chemistry too. Well, let's go up to question 18. It says, what is the major kinetic product formed in the reaction shown? And remember that kinetic products, a kinetic product is what we call the 1,2 addition product. okay, of 1,2 addition. So that means when we react with HCl, in the first step, the rich are going to get richer. We would end up doing the proton transfer, and we end up with this carbocation. So let me draw it here quickly. We have a methyl group here, and we have this tertiary carbocation, and then before any stabilization can occur by resonance, the chloride is going to come in and it's going to do a nucleophilic attack here, and that is going to give us our product. Again, this is 1,2 addition, it's kinetic addition, and we end up with this compound here. Of course, there's a stereocenter in the molecule. This is B, is the product. There is a stereocenter here, but that is not shown. And you could presume that you would end up with a racemic mixture because the carbocation is trigonal planar, right? You should know that the hybridization is sp2, and that is trigonal planar. There we go, this carbon over here. All right, what's the best reagent shown for this conversion? So we want to take an aldehyde, and we're going to reduce it to an alcohol. And you see that we're adding a deuterium. Okay, we're adding a deuterium and a hydrogen. So we can't just take it and treat it with D2, because then you would add a deuterium in both of these positions. So could anybody propose something here for this one? Remember that deuterium is it's just hydrogen 2. So hydrogen 1, that's hydrogen. And then we have hydrogen 2, which is deuterium, which is just an isotope of hydrogen. I'm going to suggest that the best answer is to use, sodium borodeuteride instead of sodium borohydride. And then methanol, okay? And it says in an aqueous workup. All that means is that in the first step, you treat it with sodium borodeuteride and methanol or ethanol. And then in the second step, you treat it with water. So let me show you what that would look like if we go over to a blank document. Okay, we have our starting aldehyde, which is cyclopentane carbaldehyde. So this aldehyde here, and then you're treating it with sodium borodeuteride. So instead of 4 hydrogens surrounding the boron, you have 4 deuteriums like this. And so we get our nucleophilic attack occurring like this. So the deuterium ends up on the carbon that's attached to the ring. So we end up with a carbon with a hydrogen and a deuterium. Then we have our oxygen with a negative charge. So this is step 1. And of course, you have the sodium cation, so we can put it over here if you really want to. But in the next step, when you treat it with water, you do a proton transfer where the alkoxide rips that proton off, and you end up with this molecule. So you have OH, and then you have a hydrogen here and a deuterium here. So this is your final product. So that's the mechanism. And everybody knows that sodium borohydride is going to do the reduction, but it's a matter of knowing, which proton comes from where, right? You need to understand that this proton or this deuterium comes from the reducing agent, the sodium borodeuteride, and that this hydrogen over here comes from the water in the aqueous workup. So it's a little bit of knowing about reduction and mechanisms. Next one, it says, what is the product of this reaction? Remember that when we have an ester that's in a ring, we call that a lactone. So we're taking the lactone and we're treating it with lithium aluminum hydride, followed by treatment with acid. Well, hopefully you remember that when we take an ester, so let's just take something like this. This is ethyl acetate, that when we treat that with lithium aluminum hydride, followed by treatment with water, that we end up reducing the ester to an alcohol, plus we would liberate this part of the alcohol as well. So you end up with 2 alcohols. And so A cannot be an answer, right? We would have to split it here. So we've only got 1 hydroxyl here. That can't be an answer. And here we have an aldehyde and a hydroxyl. So this can't be an answer. That means the answer must be D. And you can see that it's got the correct number of carbons. If we count 1, 2, 3, 4, 5. Here we've got 1, 2, 3, 4, 5, like that. And if you don't believe me, well, in that case, we could take a look at the mechanism. And this is a mechanism that we looked at in some detail earlier on in this class. So if we take that lactone, oops, we take this lactone here, right, and we treat it with lithium aluminum hydride. So I'll draw the lithium, or the aluminum hydride ion, I should say. So we'll draw the first step, which is a nucleophilic attack by the hydride. Just going to bring a pair of electrons up here, and then we end up with something that looks like this. So now we've got our oxygen with a negative charge on it, like this. I left this oxygen out. And so now this oxygen is going to behave as a leaving group. If you don't believe me, and then the hydrogen's here as well. But what's going to happen is we open the ring like this. It's going to pop open, and you're going to end up with this, where you have an aldehyde on one side, okay? And that's this carbon right here. Then we have 2, 3, 4, 2, 3, 4, 5 carbons. So we have 1, 2, 3, 4, 5. And then the hydroxyl, just let me count that 1, 2, 3. Yep. And so now you've got an aldehyde and a hydroxyl. And what's going to happen is that's going to react with another equivalent of the aluminum hydride ion. Draw that out again, and we're going to get another nucleophilic attack to our aldehyde, like this. Then we have this, and we've got this. And then after a proton transfer, once we add water in, did I add a hydrogen there when I shouldn't have? There. So we have this. Sorry, I put a hydrogen there. I had a proton transfer on the brain. But anyhow, we do 2 proton transfers, and we end up with this molecule. There you go. So this would be what? 1,2-pentane, or 1,5-pentane diol, I guess is what you would call that. Let's go back to our practice quiz. And so we figured that one out pretty quick. So it's 1,5-pentane diol. All right. Hey, polymers. I told you that we're not going to have a lot of questions on our final about polymers, but it asks you which of these polymers could be readily prepared by condensation. Remember, condensation is the loss of a small molecule. Could be water, could be ammonia, could be CO2 even. Anyhow, loss of a small molecule. Could anybody tell me which one of these would be the result of a condensation polymerization? There's only one good answer. I'd have to say it would be A, right? Because if you keep repeating, right, you would have this. Right, you'd end up with this. So you have an amide, right? And since there's an amide repeating, how do you form an amide? By loss of water. You condense a carboxylic acid and an amine, right? You start out with a carboxylic acid, right? And an amine. And that you bring those together and you end up with an amide. And so the answer would be A. All right, let's move on to 22. It says, which base should be used to quantitatively? Quantitatively is just a fancy way of saying 100% yield. So you take everything and you convert this NN-dimethylamide anion, or sorry, NN-dimethylamide into its enolate ion. So we would want to remove one of those protons. You would take this and you would treat it with a strong base, okay, and you would remove one of those protons, and that would give you this. Son of a gun, what happened there? You would end up with this. So you end up with the enolate. So you have 2 methyl groups here, like that. So what would I use? I would use the strongest base available to me. Could anybody tell me which one of these would be the strongest base? It's a base that we looked at quite a bit Yeah. Could you tell me what the acronym is for C? Does anybody know the acronym for this base? This is LDA. LDA, which is lithium diisopropyl amide. Lithium diisopropyl amide. There you go. So that's definitely the strongest base. How do I know that? If I look at the conjugate acid of all these, right? The conjugate acid of hydroxide is water, right? Which has a pKa of around 15.7. The conjugate acid of ethoxide is ethanol, which has a pKa of around 17, 18. We'll just put 17. The conjugate acid of an acetate ion is acetic acid, which has a pKa of around 5. pKa around 5. And the conjugate acid here would be an amine, which has a pKa of around 35 to 38. So pKa, we'll just put here 36, okay, which is close enough. So you can see that by far this is the weakest acid, and therefore it's going to produce the strongest base. So LDA is the strongest base of all. And that is going to do the 100% or the quantitative deprotonation of this amide to produce the enolate. Number 23, we're taking what? We're taking an aldehyde and we're treating it with hydroxide and water. And so this is going to be an aldol addition, right? If it was heat, it would be an aldol condensation. But since there's no heat, therefore, aldol addition reaction. So, I mean, we could, try and just draw the product of the aldol addition. I find these are actually easier to solve if you look at the mechanism. So let's take a quick peek. And we just learned this a couple weeks ago, so it bears repetition. So I'm going to start by drawing out the aldehyde. So we have this, and I'm going to explicitly draw this proton out because I need to abstract that proton. So we're going to take this and we're going to treat this with hydroxide. Here. So hydroxide, and then we're going to rip this proton off like this, and that's going to produce, now I'll draw a bond line structure. It's going to produce, so 1, 2, 3, 4. It would produce this, right, which has, you can draw the enolate form where the negative charge is up here, but anyhow, you get the idea. So we have the oxygen with the negative charge up here. Let me just clean that up a little bit. There we go. So this is the enolate. These are the two resonance contributors here. And so I'm just going to redraw this compound right here. So what's going to happen is, since I'm using hydroxide, I'm not going to do a quantitative deprotonation, am I? I'm going to deprotonate some of the ions. And so if I draw my enolate like this, what's going to happen is some of those enolate molecules are going to see other molecules of my aldehyde. I'll just kind of draw it like this, and we're going to get a nucleophilic attack like that, right? And that's going to give us something that looks like this. So we still have this here. Now we've got the carbon, which is going to have an oxygen with a negative charge, then 1, 2, 3, 4, like this. Then we're going to do a proton transfer, of course, right? So there's water around in the reaction mixture. So this is going to rip off a proton from my water molecule, and then I get the aldol, son of a gun, I get the aldol product, right, which has got an aldehyde and an alcohol in it. So let's draw it out. And it's going to look like this. So I have my hydroxyl here, 1, 2, 3, 4, like that. Okay, and there's nothing wrong with the way I have it drawn. It's perfectly fine, but they just have it in a slightly different orientation in the textbook, or sorry, in the solutions. They just represented it like this, where you have an ethyl group down here, and then you have, so alpha, beta, hydroxy, and then 1, 2, 3. Okay, so they basically just rotated this bond. Okay, and then again, these are the same damn thing, okay? But this is the kind of the way they have it drawn in the solutions or the quiz. Let's go back, and I think it's C if I remember correctly. Where is it? Yeah, it's C. And so again, this is just a plain old Aldol addition reaction. And if you don't have to draw the mechanism out, there's no problem. I'm very proud of you if you don't have to draw the mechanism. And if you do have to draw the mechanism, I like to do it because I find it cuts down on me making mistakes. So let's move on to question number 24. We've got another polymer. All right, we got polymers on the brain. Let's see here. It says, what monomers are needed to produce this polymer? And you notice that this is some kind of polyester, isn't it? Right, because you've got an ester. So this is a polyester. You know, you guys are studying for a polymers quiz. I'll throw this out there to my students. Can anybody make a suggestion as to what compounds you would need to make this polyester? I think that D is probably the best bet because a polyester is going to come from a carboxylic acid and an alcohol, right? So we have a carboxyl and an alcohol here. And if you react them and you lose water, you would end up with this, where you have the carbonyl, right, like this. Then you have CH2, CH2, carbonyl. Then you'd have the oxygen, CH2, CH2, oxygen, like this. And that is the compound that we're looking for. And so the answer is going to be D, would be the correct answer. Let's move on from there and take a look at question number 25. I'm just going to throw this out there to my students. I'll see if I can zoom in on just the answer. It says in 25, just what's the product of this reaction? First, I'm treating it with chlorine and sodium hydroxide, followed by water and acid. Does anybody remember this reaction? This is called the haloform reaction. The haloform reaction. So in the haloform reaction, we're going to end up converting a methyl ketone. So we take a methyl ketone and you treat it with chlorine, bromine, or iodine. So I'll just put X2 and sodium hydroxide in the first step. And let me just write down the intermediates here. So in the first step of the iodoform reaction, you end up making, from a methyl ketone, you make this. So now you've converted the methyl group into a good, this is now a good leaving group because of the induction of the 3 chlorines in this case. And then in the next step, you treat it with aqueous acid. So you basically just hydrolyze it, right? And what do you hydrolyze it to? You hydrolyze it to a carboxylic acid because you've got a good leaving group there. And so the answer is you're going to convert that into a carboxylic acid. So you're going to go from acetophenone to benzoic acid. So that is the iodoform reaction. Sorry, this one would be a chloroform, but anyhow, it's the haloform reaction. So if you've forgotten this reaction, I recommend that you look up the iodoform reaction. This is one that we covered in detail this summer semester. The iodoform reaction, a really convenient way to take a methyl ketone and convert it into a carboxylic acid. Okay. Next one, it says, which position will be attacked most rapidly by the nitronium ion when the compound undergoes nitration? So if you subject this compound to the nitronium ion, we could just draw that over here. You know that the nitronium ion is a very powerful electrophile. And so where is the nucleophilic attack going to occur from? Well, we've got a methyl group over here, and a methyl group is ortho-para-directing. So it's an ortho-para-directing group. Okay, it's also small. It's very small, so we'll put here small, and I'll show you why I'm going to write that down. Because if you look at C, position C, well, you've got an aromatic ring on here, and this is also ortho-para-directing. Okay, but it's really big. Okay, now these are also mildly activating, right? Very mildly activating. Whereas the acetyl group over here is going to be a meta-director, and it is deactivating. So we'll circle this over here. So we have this, and we're going to say this is a meta-director, and this is deactivating. Okay, but again, both of these are going to be weak activators. So we'll put activator over here and activator over here. And so the preferred position is either going to be C or D, but I'd say that since they're both ortho-para-directors, and this group is just so darn big that the nucleophilic attack is going to occur through D. It's going to occur through carbon D because it's the least hindered. So it's going to attack like this, and nitration will occur at position D. Question 27, the copolymerization of vinyl chloride and vinylidene chloride. We actually looked at this in chapter 10. Is used to make food wrap. It's actually used to make saran wrap. Which structural unit would appear in this polymer? Can anybody answer this one? Absolutely. I agree. I think it's B. I agree. It's B. And again, this is saran, the same saran that's found in saran wrap. Right? How did Skylar know that? He said, well, I've got my vinyl chloride, CH2, CH with a chlorine, right? And then I add my vinylidene chloride, so CH2 and a carbon with 2 chlorines, and that's going to be my repeating unit, which is B, like that. And that's saran. Again, it's found in saran wrap. I won't ask you about saran wrap on your exam. Let's try a redox reaction. Next one, it says, which compound can be most easily oxidized by potassium dichromate and sulfuric acid? That's just another way of making the Jones reagent, right? We always used sodium dichromate and, sulfuric acid, it's just a way to make chromium 6 anyhow. So there you go. So it's the same type of thing. So this is a Jones oxidation, which is just a very strong oxidizing agent. So which one of these could be most easily oxidized? Can anybody give me a suggestion here? I agree. I think it's D because you can't oxidize A because it's a carboxylic acid. You can't oxidize B because it's a tertiary alcohol, and you can't oxidize a tertiary alcohol. You can't oxidize a ketone any further, but you can oxidize D, can't you? If you were to treat that with potassium dichromate, again, which is just a really strong oxidizing agent, you could convert that into a carboxylic acid, couldn't you? You could take that and you could convert it into a carboxyl group, right? Aldehydes can be further oxidized to a carboxylic acid. Let's take a look at question 29. Question 29, what is the expected product of this reaction? Let's zoom in on it here. You got this interesting compound where you get 2 chlorines on the ring. You get a nitro group here and a nitro group here. Look at this. You're treating it with 1 molar equivalent of sodium methoxide, which is a strong base, but it's also a good nucleophile. And look at this. We've got 2 good leaving groups, right? Chloride is a good leaving group. But remember, if we wanted to do an SN-AR reaction, remember that the leaving group has to be either ortho or para to a strongly electron withdrawing group. And we have 2 strongly electron withdrawing groups here. The problem with this chlorine is that it's meta to both of them, whereas this one is ortho and para to the both. Right? So what's going to happen is that my sodium methoxide, my methoxide ion is going to do an SNAR reaction, right? It's going to attack this carbon, and I'm not going to draw the entire mechanism and draw the Meisenheimer complex and all that. But if you have to review that, it would be a good idea. So this is nothing more than an SNAR reaction. And so you're going to substitute that chlorine for a methoxy group. And so the answer would be C. Again, if you need to review this, it is the SNAR reaction that we looked at in detail in chapter 18 when we discussed electrophilic aromatic substitution. Question number 30, what is the main product of alkaline permanganate oxidation after neutralization? Well, we're taking propylbenzene and we're treating it with potassium permanganate in sodium hydroxide, which is really, really strong oxidizing conditions. So we oxidize at the benzylic position, right? This is a benzylic oxidation. So after the first step, right, after step one, what you actually end up doing is you oxidize that to a carboxylate. Sorry, that was calling me. So you oxidize to a carboxylate after the first step, but then in the second step, you treat it with aqueous acid and you do a protonation to form the carboxylic acid. Oops. Draw that a little neater. There we go. So we end up making benzoic acid, which is this compound here. Now, if you're wondering, well, what happened to these two carbons? They just go away. They're going to end up in the waste because this is a benzylic oxidation. Benzylic oxidation. Ooh, let's get into some spectroscopy. Now, remember, you're not going to have the handout for spectroscopy. Okay, you're going to have to use your wits and your prowess with respect to spectroscopy. So let's take a look here. It's question 31. Which structure is most consistent with this infrared spectrum? So remember, sometimes we like to draw lines on the spectrum. So sometimes it's handy to draw one around 3,000. Oops, my ruler's not very good, but anyhow, close enough. And then I like to draw another one around, I don't know, 1,600 can be helpful, or let's do 1,700. Let's do right, son of a gun. There we go, close enough, okay? Anyhow, there we go, those two lines. Does anybody recognize what these would be up here? I have two, medium to weak signals up here, two peaks. Yeah, exactly. This is a primary amine. All right, so I've got a primary amine. So that means I can cancel this one out. So I'm down to 3 compounds. Well, the next thing I would look for, right? I like to look for low-hanging fruit. Is the compound aromatic? Yes or no? So let's go over here and determine if the compound is aromatic. And when I look around the aromatic region, remember that for a compound to be aromatic, between, let's say, 1475 to what does that say, 1600-ish, somewhere around here, you should see some you should see some signals here. So these would be the aromatic carbon-carbon stretching. Sorry, I'm just kind of looking at this thing since I didn't bring in the solutions or anything. So this is aromatic. That means that we could cancel this one out. So there we go. Now to discern between B, if we're trying to pick between B and C, so that I think I have it figured out now. It could be either B or D is the possibility, right? This is not aromatic, so that's not an answer. and it's not a, and this one's not a primary amine. So it's either B or D. Could anybody tell me how you would discern between B or D? And it's not a trick. It's actually easier than you would ever probably even imagine. Is that the difference is that D has sp3 hybridized carbon-hydrogen bonds, right? You have sp3 carbon-hydrogen stretching, whereas here you have no sp3 carbon-hydrogen stretching. Now, where does that come? Just below 3,000. And so since we have absorbances right below 3,000, we usually don't even label these because they're just so ubiquitous in organic chemistry. So since we have those sp3 hybridized carbon-hydrogen stretching, the answer must be D. And that's it. That's how we solve that. It's actually a little less complicated than I thought it was when I first glanced at it. All right, let's move on to question 32. It says the chemical shifts in the carbon-13 NMR spectrum for this compound are 15.8, 40.1, 51.8, and 170.2 parts per million. Which is the correct set of chemical shifts for the carbon atoms? Well, if I look at these, I mean, the easiest thing to do would be to, again, go for the low-hanging fruit. Could anybody tell me which one of these would have the lowest chemical shift? Which one do you think would have the lowest chemical shift of all? Would it be carbon 1, 2, 3, or 4? Yeah, it's going to be carbon 4. So this one is going to be the less deshielded, so this will have the lowest shift, which would be 15.8. Could anybody tell me which one would have the highest? I agree. The carbonyl is definitely going to have the highest. The highest, which is what? 170.2, 170.2. So that means 2 has to be 170.2, and number 4 has to be 15.8. So the answer must be D. And just like that, we solved that one. So that one we kind of did by process of elimination, but a lot of problems in the final exam can be solved that way. Question 33. Which of these two compounds will show two triplets among other signals in their NMR spectrum? So two triplets. Okay. Let's see here. If we zoom in on this a little bit, I'll start on compound number 1. So we have no symmetry in the molecule because you have 2 chlorines here and you only have 1 here. So if we examine each one of the protons, right, these 2 protons are coupled next to these 2 protons. So they're going to give you a triplet. These 2 protons are coupled next to the 2 protons in the red circle and this proton in the green circle. So that's actually going to give you a triplet of doublets or a doublet of triplets or something like that. We'll just call it, we'll call it a multiplet. Okay. And if you look at the next one, the one in green, it's coupled next to the 2 protons in blue. So that's going to give you a triplet. So there you go. Number 1 must be a possibility. It's definitely going to give you 2 triplets. Number 2, let's see. Number 2 is, it's got a plane of symmetry, doesn't it? Right? Because this is identical to this, and you get a methylene. So let's circle these 2 protons, which are coupled next to the 2 protons I'm going to put in the yellow circle. And the 2 protons in the green circle will give you a triplet because they're coupled next to 2 protons. So this is a triplet. These protons are chemically equivalent to the other protons in the green circle. So these are going to give you a triplet, but these 2 triplets are identical, right? That triplet would integrate for a total of 4 protons. And then the yellow protons, those are coupled next to 4 protons. So that would actually give you a quintet. So this one only gives you 1 triplet. Okay, because the 2 triplets are overlapping, they're chemically equivalent. So number 2 is not a possibility. So 1, okay, so I guess we have to look at number 3. We have to do the whole thing. And number 3 has symmetry in the molecule too. So we'll start by examining this one here, which is coupled next to the 2 protons I have circled in red. So the proton in blue will give you a triplet. So this will give you a triplet, as will this. Right? It's the same triplet as the other one. They overlap. And the one in red is coupled next to 2 protons. 2 plus 1 gives you a triplet. So here we go. So the answer is 1 and 3. Right, in number 1, you have the triplet that I have highlighted in red and green. And in 3, you have the triplet in blue. Again, these are identical. So these are the same triplet. And then you have the 1 in red. And so the answer is what? 1 and 3. There you go. 1 and 3 only. Perfect. Not too bad. Next one. What is the major product of this reaction sequence? All right. Well, let's give it a shot here. We've got propyne. And after step 1, okay, we're going to treat it with sodium amide. So that would give us the alkanide. This goes all the way back to organic chemistry 1. In step number 2, we're treating it with methyl bromide. So that means it's going to react with the methyl bromide, which is a very powerful electrophile. And you're just going to do an SN2 reaction like this. So that would give you this compound. So it gives you 2-butyne. And then in the last step, to give you the final product, you do a Markovnikov addition of water using water, sulfuric acid, and mercuric sulfate. Now, there's no Markovnikov or anti-Markovnikov to worry about here. And so you would end up with this, where you have, let's just put the hydroxyl here, double bond, like that. And that's an enol, but that enol is going to undergo tautomerization, won't it? And when it undergoes tautomerization, it's going to give us what? It's going to give us a ketone. And the ketone that it's going to produce would be A. Yeah, it's going to undergo tautomerization. So you're going to rearrange the double bond and the proton. So you end up with this, where you have CH3 carbonyl, CH2, and CH3, which is A. There it is. So this is butanone. There we go. All right, and this is this is Markovnikov addition using, this is Markovnikov addition of water across a triple bond, right? Because you need the mercuric sulfate to affect that process. Number 35, which sequence of reagents will accomplish this transformation? So we're taking paramethylanilin, and we want to install 2 bromines. Well, we know that when we have the nitrogen on the ring, it's so activating that when we treat this with bromine in the first step, it's going to just activate the whole damn thing, right? So if you take this compound, let me just scribble it down here for you. If you take that compound, and we looked at this in detail in our chapter on electrophilic aromatic substitution, we said if you take this compound, you treat it with bromine, you don't even need a Lewis acid, my friend, right? The nitrogen is an ortho-para director, and it's very powerful, and so that's going to completely brominate at the 2 ortho positions. It would do the para position, but it's blocked by a methyl group. So then how do we remove that amine? What do? Is we do diazotization, don't we? We treat it with sodium nitrite in HCl, and here it says 0 degrees Celsius. That's going to give you the diazo compound. And we looked a lot at diazo compounds. We studied Sandmeyer chemistry. This is not a Sandmeyer reaction, but we studied them. So you have the methyl group down here. And then to remove it, in the last step, you treat it with hypophosphorus acid. So you treat it with H3PO2. So this is hypophosphorus acid. And there you go. That's all there is to it. So this is diazotization. So if you need to review that, be sure to review your diazotization chemistry. It's very important. And then we have one last question here. It says an unknown compound was found to be unreactive towards chromic acid. What does that tell you? You can't oxidize it. So if it's unreactive to chromic acid, so cannot be oxidized. Okay, and then it gave this IR spectrum. So you can clearly see that there's an alcohol in the compound, can't you? But if you take the old ruler draw a line here around 3,000. It's not the greatest line, but anyhow, you can clearly see that there's an oxygen-hydrogen stretch. So we have an alcohol. Now, if the alcohol can't be oxidized, it can't be this because it's an ether. It can't be a primary alcohol because that can be oxidized. It can't be a secondary alcohol because that can be oxidized, but it could be a tertiary alcohol, couldn't it? So that kind of narrows it down really quickly. And does the rest line up? Absolutely it does. Right? You see that between, around the 1475, to 1600, we have some carbon-carbon stretching here that's aromatic. We have the overtones here, okay? We have oxygen hydrogen stretching maybe here. This might be carbon oxygen stretching here. Either way, you could see how you could solve that problem by a process of elimination pretty darn quick. In fact, you don't even need the spectrum. The only reason you would need the spectrum is to see that there's an oxygen hydrogen stretch, which would allow you to differentiate between A and D. Really, it's the only thing, because those two compounds both won't be oxidized. All right.